And we're going to get back in and we're going to start talking a little bit more about atomic theory. And so where we left off last time was we were talking about protons, electrons, neutrons, and how they make up the atom. And so when we get to this point, we have been talking about this. And now I'm going to move into sharing my screen. Okay. So we talked about atoms being made of protons, neutrons, and electrons. And we described a nucleus of an atom as having protons and neutrons contained within in a nucleus, and electrons in a cloud around it. And maybe we want to show that right now as orbits. And the only reason we might want to show that as orbits right now is because it's convenient. It's convenient. We know that it's not actually the correct way to look at it, and that electrons don't actually orbit. We're going to talk a little bit more about that later. But what we want to get to is this. First of all, this is not to scale. If you check out that video a little bit, remember it's called Ultimate Zoom. If you want to go look at it again on YouTube, remember this is not to scale. Remember, we can't see the nucleus once we've zoomed out to the point that we can see the outermost electrons. The nucleus is not visible. And so what we want to get at is that the outside of the atom to the nucleus is essentially empty. There's nothing there. It's literal nothingness. No particles, no existence at all. We talked a little bit about the properties of these subatomic particles, protons, electrons, and neutrons. What did we say about neutrons? They have 0 charge, and they have 1 AMU of mass. And we talked about protons. They do have a charge. Protons have a +1 charge, and they have 1 AMU in mass. We talked about electrons as well. They have electrons have a -1 charge, and on the order of 1 significant figure, their mass is 0 AMU. And so all of the mass of an atom is centered in its nucleus. And so if you want to see how we came to this conclusion with scientific experiments, then what you want to look up is Rutherford's gold foil experiment. I won't draw it, but in a sense, what we're going to do is we're going to have a detector, and we're going to put a sheet of foil in the middle of that detector, and we're going to shoot some things through that sheet of foil. The detector is going to be all around it, except for the little hole where we're shooting things through. By and large, the detector says when we shoot things through, they just go right to the other side, like that sheet of foil isn't there. But occasionally, something bounces back, like it hits something hard. And what you're to gather from that experiment is that it's because the atom itself is essentially empty space. If we're shooting small particles like through these atoms, then there's really nothing to hit, except for occasionally you do manage to get to a nucleus, in which case then it bounces back. So if you want to check that out a little further, that's the gold foil experiment. That's how we first started to get an understanding of what's going on inside of an atom. Okay, we talked about the properties of protons, neutrons, and electrons. We talked about their charge, and we talked about their masses, and we also talked about an atom is defined based on the number of protons. So let me give you an example. Here's the example that I want to give you. Carbon has 6 protons. What does this mean? It means that the atomic number of carbon from the periodic table of elements equals 6. What did we say about neutrons? We said that neutrons can vary. So if I'm going back to this carbon, so carbon, for example, it always has 6 protons. It doesn't matter what we're talking about. But one version of carbon might have only 5 neutrons. Another version of carbon might have 6 neutrons, and another version of carbon might have 7 neutrons. And so and that's exactly right. When we talk about neutrons having the ability to be varied inside of an atomic nucleus, what we're saying is that the number of protons is very much what determines the name of the atom. 6 protons, carbon, end of story. But with those 6 protons could come a varying number of neutrons. And so this is what we mean by isotope. An isotope very much is the same number of protons, but a different number of neutrons. So when I talk about the 3 possibilities for carbon, the vocabulary word is used like this. I am referring to 3 different isotopes of carbon. Or I could say carbon is found in with 3 common isotopes. Now the truth is that most every atom has a varying number of isotopes. For instance, hydrogen comes in 3 different isotopes. Hydrogen with just 1 proton in it, because if you remember, hydrogen has atomic number 1, so that means there is 1 proton. With the 1 proton, we can have 0 neutrons, or we can have 1 neutron, or we can have 2 neutrons. And so there's 3 flavors, 3 isotopes of hydrogen. But something like phosphorus has like 7 isotopes. And so the number of isotopes does change just based on the atom. But most atoms, essentially every atom, has at least 2 isotopes. Now, what we're going to get to at the end of this discussion is something called the natural abundance. And what we want to get our head around is this idea that if I'm talking about the 3 versions of hydrogen, they're not in the same abundance. In other words, briefly, what I'm saying is that 99.97% of all hydrogen is just protons, 0 neutrons. Another 0.02% of it is 1 proton, 1 neutron, and 0.001% is 1 proton, 3 neutrons. So it's a vast difference in the abundance, and we'll get to that a little bit more in a second. What we're starting to do is we're starting to get a little bit of information about an atom and its atomic structure. So now that we know that there are the possibility to have, we can change the number of protons, which changes the atom that we're talking about. But we're also can change the number of neutrons, which changes the isotope that we're talking about. And also we need to get our head around the possibility that an atom might not have the same number of electrons. And so let's talk about that now for a second. Well, remember that we said that the electron has a -1 charge, and the proton has a +1 charge. Well, let's take a look at helium. because I only want to draw 4 dots, 2 neutrons, 2 protons, 2 electrons. If I were to talk about the charge of the atom itself, then what I would need to do is add up the charges of all of the individual particles. Excuse me. If helium has 2 protons, then that means it has 2 particles with a +1 charge. So from the protons, I get a total of +2. What about the electrons? Well, if I have 2 electrons, I get 2 particles with -2. So then what's the overall charge? Well, the overall charge, +2 -2. I know that's really difficult math, but 2 minus 2 is 0. Can I get a 1 in chat for being ridiculous? Yeah, I appreciate that. Somebody's paying attention. So somebody else. I appreciate that. Anyway, all right, now let's move on. Let's move on. Yeah, okay. The fact of the matter is that sometimes atoms which are neutral overall, right? An atom is neutral overall because typically it has the same number of protons as electrons. But they can gain or lose electrons and become charged. There's a word for something that is charged from the perspective of a chemical species, and the word is ion. It's a chemical species that is charged. Yeah, and so the question is asked, are we going to get into cation and anion? And we are, certainly, right? Because if a species is charged, what could it have done? It could have gained or lost electrons. If it gained electrons, then what does that mean? It has more negative charge than positive charge. If it has more negative charge than positive charge, then that species is negative. If it loses an electron, then it has less negative charge than positive charge, and then that means that species has a charge, and that charge is positive. And so we actually have names for that. A cation is a positive chemical species, and an anion is a negative. And of course, we're talking in both cases in terms of charge. Okay, in terms of charge. So again, if you lose or gain electrons, then you become charged as a chemical species. And a chemical species that has a charge is called an ion. The particular flavor of charge can be positive or negative, and the thing that has a positive charge is called a cation, and chemical species that have negative charges are called anions. One of the things that you're going to have to do in nomenclature is learn how to name species that have positive and negative charges. So let's kind of review really quick. Let's go back to the example of carbon. And what I want to do is I want to introduce a new symbol or a new way to look at a particular bear with me one second. So this is the way we want to represent all particular atoms when we're really trying to dig down and specify their particular isotopic composition. And so what do we have here? Z equals the number of protons. It's also the atomic number. And remember, the atomic number is from the periodic table of elements. A is the mass number, and it's essentially the number of protons plus the number of neutrons, right? So how could you figure out the number of neutrons that an isotope has? Well, you take the number, you take A, the mass number, and you subtract from it the number of protons, and then you'll have the number of neutrons. And we'll go through an example. On this side, what I want to include is the charge, if any. And you'll learn that by convention, hold on, I actually have to write it. Yeah. By convention, it's, we put the number before the charge. So value before charge. So we would say 2 plus or 3 plus or 2 minus, not minus 2, not minus 3, etc. And it's just a convention. Everybody will know what you mean if you say plus 2. Okay, and so let's kind of put it together. Let's go back to that carbon. So carbon has 6 protons. If we're talking about the carbon that has 6 neutrons, then what is A equal? If we're talking about the carbon that has 6 neutrons, then what does A, the mass number, equal? Remember, the mass number is the number of protons plus the number of neutrons. It's the number of protons plus the number of neutrons. Right. It's 6 plus 6, which is 12. Yeah, now we're starting to get it. What's the symbol? How do I sort the symbol out? Well, this is what you do. You go to the periodic table, you look for the thing that has atomic number 6, and you write down the symbol. And so what I want to do real quick is I want to take a look at a periodic table. Let's try to find a nice high resolution periodic table. Just give me one quick second. This one looks like it's high res. It was high res. Here we go. So I'm going to stop this share real quick. I'm going to jump into this share real quick. And so what you see here is a periodic table. And so and it's really hard to see, but you see what you see is the symbol, the name, and the atomic number. And so what you want to do is become familiar with the periodic table because it's going to be your best friend. Let's see if I can see another version that's a little bit more straightforward. It's really hard to find high resolution periodic tables. Here's one. Oh, here we go. And so you see that, again, it's not high res, but there's the atomic number of fluorine, carbon, so on and so forth. And so remember that the atomic number is the number of protons. So carbon has 6, nitrogen has 7, oxygen 8, fluorine 9, etc. So let's go back to this one. Go back to our carbon. So what would the charge of carbon be? Let's say that it gained. All right, well, first of all, how many electrons does carbon need in order to be neutral? How many electrons does carbon need in order to be neutral? Right, the number of electrons has to be the same as the number of protons. The number of electrons has to be the same as the number of protons. And so if I want to make them the same, then that means the number of electrons has to be 6. The number of electrons has to be 6. Uh-oh. Uh-oh. There we go. Okay, let's stop messing around. Okay. What happens if it gains an electron? What if it has 7? What's its charge then? What would its charge be? Right. It would be 1 minus, exactly. And by convention, we never write the charge, the value. We don't write the value if it's only 1, right? So a single negative sign means 1. Okay, let's keep going with this. What if it actually had gained 4 electrons? How many would it have? If it gained 4 electrons, how many electrons would it have? Let's think about that for a second. If it has 6 in order to be neutral, then it must have, if it gained 4, then it must have 10. Okay, we're doing good. Now let's think to ourselves, if it has 10, what's its charge? And remember, by convention, I'm going to put the number first, 4 minus. Exactly. All right. So let's revert to something that would be 4 plus. How many electrons must it have in order to be 4 plus? How many electrons must it have in order? Right. It lost 4 electrons. So if it starts with 6 when it's neutral and losing 4 electrons to become 4 plus, it must mean that it only has 2. What happens if I change the number of neutrons to be 7? What do I change? What part of the symbol do I change? Yeah, and let's be specific. And I want to just point out that it really is called the mass number. And so I know that you know what you're talking about when you write down mass, but the vocabulary in this particular case is different or is important because we're gonna use the word mass to refer to something else. So We really want it to be correct. Protons plus neutrons. It's the mass number. So the mass number changes. What does it change to? Yeah, right. It's 13. It's 13. Okay, so you really ready for the real trick question? What do we call carbon with 7 protons? What do we call carbon with 7 protons? Most folks are saying what I'm hoping that you're saying. Remember that the number of protons determines what the atom is. So once you have said, I have 7 protons, it's just not carbon anymore. It's now nitrogen. So that's the trick question. And so this is a common mistake that students make. When we talk about ions and you're first learning about it, you think to yourself, well, if I add a proton, then I just must have a positive charge now, so I'm carbon with a plus. But you have to get back to the basic definition of elements and what their properties are, and remember that the number of protons determines the element. So what I tell my students is this: when you're thinking about particles, anchor yourself in the idea that the number of protons for a particular element just doesn't change. The only thing that we can change for a particular element is the number of neutrons to make it a different isotope, or the number of electrons to make it a different, to make it an ion. Once we start fiddling around with the number of protons, now it's just some other element, and we just start over with our consideration, right? So what do we call carbon with 7 protons? There isn't carbon with 7 protons. There's no such thing. Something that has 7 protons is some species of nitrogen, right? And so I just want to make sure that everybody's clear on that, right? All right. So we're kind of getting to the end of it. Kind of getting to the end of our time together too. So I want to move that over here off to the side, maybe get rid of it completely. And I want to go back to the periodic table, because there's some things that we have to know about the periodic table. And so here's my fake periodic table. And I'm only going to do a couple of different things. What I want to do is I want to show the reader some different regions in the periodic table. And you have to know what their names are. And so I'm drawing some of the important features that you'll see in the periodic table. It's not perfect, it's not to scale, but it gives you the right idea. All right, in general, I can divide the periodic table into 2 sections. All of this is called transition metals. Transition metals. The other parts of the periodic table are called main group. And that includes over here too, main group. I spelled transition wrong. I know. I knew I did. And since I'm going to put it up on YouTube, I want to correct it because I only want to embarrass myself a little bit. I only want to embarrass myself a little bit. Clear. What's clear? We good? Okay, cool. So this is like the main sort of way to sort of break down the periodic table. All this stuff right here in the middle, transition metals. The two other things on the other sides are called main group. I want to back up. Oh, there's my misspelling again. Let's see if I can get rid of that as quick as possible. And let's talk about some specific pieces. The periodic table is broken down into groups and periods. Groups are columns. Our periods are rows. So groups are columns and periods are rows. Okay, let's go back. And so now what I want to do is I want to get at a couple of particular groups. This one is called alkali metals. And this one is called alkaline earth metals. This is group 1. And this one is group 2. Okay, there's a couple of other groups that you need to know. And they start here, group 17 and group 18. Let me shrink this down just a little bit. 17 and 18. Group 17 are called halides. And so if you look at group 17, what's in group 17? Chlorine, bromine, fluorine, iodine, not in any particular order. What's group 18? These are called noble gases. And so things like neon, radon, argon, etc. All of those things are noble gases. And so that's what you need to know. Now, there's one last little bit, and this is sort of a different generalization. And so I want to actually get rid of this version of it. I want to create a new one. Remember, it's not to scale. So I want to go ahead and get rid of this. I want to make it a little bit bigger. And then I'm going to do this little line thing again. And I want to point out this section. These are non-metals. All the rest of this business, all of this is all metals. So there's two major sections, and I prefer to say the two major sections are the non-metals and the metals. Now, there's another way to look at it as transition metals and main group, and that's all about which ones we typically see in doing chemistry. But at the end of the day, I also want you to know that there are metals and non-metals. The non-metals are all over here, but it also includes hydrogen. Hydrogen actually can be metallic or a nonmetal. It actually does both things. We're not going to talk about that extensively, but what we say is that hydrogen can be both a metal and a nonmetal. So when you specifically think about nonmetals, you should reach over to the left and bring in hydrogen into the game, because hydrogen can be a nonmetal too. Now let me back up just a little bit, and let's think specifically. In this case, I'm specifically talking about these atoms that are directly on either side of this line. These particular atoms are in the transition between metals and nonmetals. And so they have their own name too. They're metalloids. So they sort of have a mix of properties. But any atom, any element that's directly on either side of this zigzag line is a metalloid. So the nonmetals are over here. The metals are all over here. Don't forget to bring in my hydrogen into my nonmetal game. And then this little subsection, those are the metalloids. And so this is just kind of introducing you to the periodic table. And so again, remember, it's organized in groups. Groups are the columns. And it's organized in periods. Periods are the rows. We don't have special names for any period except for the breakouts that are down here. And these are lanthanides and actinides. We don't have names for periods except for the lanthanides and actinides. We really have names for the groups. And the groups are alkali metals, alkaline earth metals, halides, and noble gases. Those are the four that you definitely have to be able to identify. Alkali metals, group 1, alkaline earth metals, group 2, halides, group 17, and group 18 are noble gases. And you really know the number of the group based on the number above the column. It actually, on the periodic table, all of this stuff will be numbered. The word semi-metal is not used as far as I know. And if it is, then I believe somebody's using it wrong. They're called metalloids. All right, and so in the next 5 minutes, what I want to do is I want to introduce the last topic, and on the next time we meet, we'll finish off this topic, and this will be the last topic for the exam, and when we meet, we'll finish it off and do a little bit. Yes, group 17 is halogens. The other word is so halogens are halides, and you'll have to forgive me. This is my orgo nomenclature. I teach organic chemistry, so I'm constantly in organic chemistry land. And so halides and halogens are the same thing. This is just the difference between Gen Chem and orgo language. And so again, let's go back. Group 17, probably in the book, is halogens. Halogens. But you'll hear me often say halides. And I think specifically halides probably refer to the ions of halogens, but I'm always saying halides because of my orgo teaching. So I'm sorry if I brought any confusion in. In introductory chemistry, we should probably stick with the word halogens. There's probably a really nice circle in there somewhere. Does that clear it up? Okay. All right, so here's the last topic. It's atomic mass. And the atomic mass is a weighted average of the mass of all isotopes. And the weighting is done by natural abundance. And so let's see if we can sort this out. I'm going to do one quick example and then we'll be done. So if you look at the periodic table, you get that the atomic mass of hydrogen is 1.008. And for now, we're going to use AMU. So let's see how this works. And I don't actually know the natural abundance of hydrogen. I'm going to just kind of guess, and I'm going to say that hydrogen 1 is 99.98%. Hydrogen 2 is 0.017%. No, yep, okay. And then hydrogen 3 is equal to, let's see if I got this right. So that'd be 3 and an extra 1, 0.3%. Did I get that right? I think that all adds up to 100. Let's just do it real quick. 9.99.98 plus 0.017 plus 0.003. Did it. 100. Good. Okay, great. All right, so how does this work? Well, so remember that roughly the mass, and this is very rough, the mass of a neutron equals 1 AMU. The mass of a proton equals 1 AMU. And at this level, we can ignore electrons. So then what's the mass? So this is the abundance. So what's the mass of hydrogen 1? The mass is 1. What's the mass of hydrogen 2? The mass is 2. What's the mass of hydrogen 3? The mass is 3. So how do I do a weighted average? This is how I do it. The weighted average is going to be the mass of the first one times its decimal equivalent of its abundance plus the mass of the second one times the decimal equivalent of its abundance plus the mass of the third one times the decimal equivalent of its abundance. This is the atomic mass of hydrogen. This is how we do the calculation. We take the abundance, we turn it into its decimal form, we multiply it by its mass, and then we'll add up each of those components. And so if we do that, what do we get for the first term? 1 times 0.9998, and we get, and I'm going to do it up here, we get 0.9998 plus the next term, 2 times 0.00017, we get 0.00034 plus 3 times the next term, 0.00003, and we get 0.0009. And so let's add these all up together. I get 1.00023. And I need to get some sig figs in there. I'm going to make a little note. Sig figs. They're wrong at the moment, but I'm going to leave it just like this for illustrative purposes. I didn't get the abundances exactly right because I just made them up off the top of my head. But I think what you need to get at is that each isotope contributes its proportional mass based on abundance to the overall atomic mass. So I'm going to stop there.